Today we're going to look at game theory. Game theory is a mathematical model that helps in strategy building and analysis, as indicated in the notes. So basically what we're going to be doing here, we're going to be looking at every business scenario that we can face in terms of a game. Okay, it's not going to be in a joking way, but this is a serious matter, because when you talk of a game has winnings and also has losses. There are those who win and those who lose. So the players in this game are the people who are making decisions. People who are making decisions are the ones who are called the players. Okay, and we are going to look at the different ways in which one player can win against the other player. Okay, and we're also going to be able to look at the different ways of analyzing strategies raised by different players, and how those strategies can raise a particular outcome. Okay, the outcomes we are talking about here are what we shall refer to as payoffs in a game. Alright, so probably before I proceed, let me take you through the different technical terminologies that are going to be useful in the discussion of game theory. Number one is a strategy. A strategy. Now, what is a strategy? A strategy is the course of action. It's the way you want to achieve your success. So you are in a business environment. You're in a situation you're supposed to make a decision. So the way you make that decision, how you achieve your final goal, is what we call a strategy, a course of action. So every player, in this case, every decision maker, has a strategy. Okay, so in game theory, our first assumption is that you cannot become a player if you don't have a strategy. Okay, you cannot become a player if you don't have a strategy. Now, that strategy is what now helps you to win or to lose. If you apply the strategy successfully, you will win. If your opponent applies a similar strategy probably against you and somehow has more resources than you in one or the other, then automatically you will lose. And therefore the opponent will win. So in the process of losing and winning, there is what we call the payoffs. Okay, the payoffs therefore are the resultant effect of your strategy. Okay, the payoffs are what we refer to as the gains and losses in a game. So the gains and losses in a game are what we shall refer to as a payoff. Take an example like this kind of a situation here. We have player A and player B. So we have a strategy 1 and strategy 2, strategy 1 and strategy 2 here, whereby this is strategy 1 for player A, same strategy 1 for player B. So they are trying to apply the same strategy. Now the payoffs are in such a way that the first payoffs here, these are payoffs. This first payoff is for player B from this side here, and the second payoff is for player A from this side here, as a result of both of them applying strategy 1, strategy 1. In the case player B applies strategy 1 and player A applies strategy 2, that means the payoffs will be here, whereby player B will get a payoff of 4 and player A will get a payoff of 10. Now, when player B applies strategy 2, whereas player A applies strategy 1, the payoffs are also these ones here, whereby player B will be able to receive a payoff of 13, okay, as a result of the strategy, okay, whereas player A will receive a strategy of 1. And similarly, when they both apply strategy 2, they'll get a payoff of 7. What does this mean therefore? It means that whatever strategy of one player, whatever strategy one player applies will also affect the strategy of the other player. Okay, so there are strategies that can be very favorable on one player rather than the other player. Okay, that's why you can see the strategy may be the same, but when the combination of strategies change, the payoffs also change for both players. Now, in game theory, what we always do, like this is a scenario here of player B and player A, we always consider a scenario whereby we want to make sure one player wins. In other words, when you're making a decision, you don't base on both players at the same time. No, you place yourself on one player. In other words, you take a position of one player against the other player. So when you're making a decision, therefore, you assume to take the position of one of the players, not both of them. So if you take that particular situation, our scenario most times is based on focusing the decision maker in game theory should take the position of the horizontal position in terms of roles. In this case, if I'm the decision maker and I'm the one solving the game theory, I'll take the position of player B. Now, if that is the case, therefore, my matrix will change to what is in yellow here. This matrix here will change to that particular position. Reason being that now I'll ignore the payoffs of player A, I'll focus on the payoffs of player B. In which case the payoffs of player B are 9, 4, 13, and 7, which are the ones you see here. Okay, so in other words, my focus is on player B winning, okay, against player A. Okay, because player B now is my position as a decision maker in the game theory. Which means the payoffs of player A are now ignored. We shall focus on payoffs of player B. What does this mean, therefore? It means that, for instance, if these were customers being targeted and the total number of customers is 14, when you apply strategy A, that means player B will get 9 customers and player A will get 5 customers. If you apply strategy 2 vis-a-vis strategy 1 for player B, okay, player B will get 4 and player A will get 10. If you apply strategy 2 against strategy 1 of player A, that means that player B will get 13 and player A will get only 1. And if both of them apply strategy 2, they'll all go home with the equal number of customers, that is 7, 7. Alright, so now, when a player A gains a 7, that means player B loses 7. But since our focus is on player B, we shall now consider player B gaining and player A losing. So in this case, if instead of player A getting 14 here, we'll get 5 in the first scenario, that means player A will be losing 9. That's what is reflected here. It says that in this particular payoff, the reduced payoff is in such a way that player B wins and player A loses. So in this case, for strategy 1 and strategy 1, player B will gain 9 and player A will lose 9. In the strategy 1-2, player B will gain 4 and player A will lose what? 4. In strategy 2-1, player B will gain 13, player A will lose 13. In strategy 2-2, player A will lose 7 and player B will gain 7. Now, this kind of matrix in the yellow side, the yellow color, is what we call a zero-sum matrix. A zero-sum matrix in the sense that the gain of one player is a loss to the other player. Okay, so again, a zero-sum matrix is mainly used so that we can be able to focus our energy on one player as we are solving our game theory. Okay, it's not always the case, yes, but for the purposes of ensuring that you take position in your game theory analysis, you cannot take positions of both players. You must take position of one of the players. So we take position of one of the players, and therefore we can be able to proceed and be able to solve the game theory. In that context, I'll take you now to the strategies. The fact that there is a need for you to win as a person solving the game theory, you need to look at the strategies. So when you look at strategy here, we talked of strategy 1 and strategy 2. There's a possibility that the player B and player A may use only one of the strategies and they ignore the other. Okay, so in this case, for instance, if I take only player strategy 1 and I ignore strategy 2 for player A, that means I'll be referring to as a pure strategy. That means strategy 1 has probability of 1. It means there's a certainty that I'm going to use strategy 1. But there's a possibility I don't know which strategy I'm going to use. In this case, I'll be using either strategy 1 and strategy 2 in different proportions. So if I use both strategies, then I'm talking of a mixed strategy scenario. That's what I'm explaining down here. So we're talking about pure strategy. This is a single strategy that each player prefers to take since it maximizes the minimum gains of one player and minimizes the maximum losses of another player. In other words, probability of strategy 1 plus probability of strategy 2 is equal to 1. But if we're talking of only one strategy, okay, that means one of the two strategies will have to take probability of 0 because it will not be used at all. So that's the scenario we see here. Okay, we see here that probability of strategy 1 is 0, the probability of strategy 2 is 1, and this is what you consider to be a pure strategy. Okay, this is very common when you have a saddle point. You're going to explain saddle point in a few minutes. It's actually here. Now, a saddle point is a point in the game theory at which the minimax value and maximum value are equal. Now, what's a minimax value? A minimax value is considered to be a value, a minimum value, okay, of maximum losses. Okay, a minimum value of maximum losses that a player may may be able to realize. So take an example like this scenario here. Player A is a loser here because we want player A to lose and we want player B to gain. That's why we have taken only gains of player B and ignored the gains of player A. So in such a scenario, therefore, player A is a loser. Being a loser, we're trying to minimize the losses. In other words, if player B wins 9, player A loses 9. If player B wins 13, player A loses 13. If player B wins 4, player A loses 4. And if player B wins 7, player A loses 7. So because player A is always losing, we shall want to minimize the minimize the maximum possible losses. But in the player B is set to win. But in the process of player B trying to win, player A will try to stop player B from winning. So there are some gains player B is about to get, but these gains are considered to be the minimum possible gains. So in the process of maximize the minimum possible gains, we arrive at what we call a max-min value, maximizing the minimum possible gains, and that's a scenario we call max-min value. So when the max-min value and minimax value are the same, then we talk of what we call a saddle point. Okay, a saddle point, and each saddle point will be able to lead us to what we call the value of the game. The value of the game. The value of the game is the maximum possible payoff to one of the players, in this case player B. Okay, regardless of whatever strategy that player A may use. Okay, so we are going to look at that value of the game in the computation. Okay, so we have talked about mixed strategies already. I just explained mixed strategies. So these are sort of when it is not possible to have pure strategy. In other words, you are going to use more than one strategy to solve a game theory challenge. We have talked about a player already, so you can read about it there. There's a player. Then there's something called a Nash equilibrium. There's another terminology which is very, very key. A Nash equilibrium is a type of equilibrium it's equilibrium in game theory, which exists in such a way that two players have a strategy, okay, but they don't wish to change their strategy because any other possible strategy that may exist does not lead to additional utility or additional value. Okay, so they are aware there are other strategies that may be there. Okay, but because these other strategies may not lead to additional value, they don't choose them. Okay, they don't choose them simply because these other strategies will not change their current state of economic value. So they will stick to their existing strategies because the existing strategies will provide them with the most sensible economic value in the particular situation they are in. Okay, so every player wins because everyone gets the outcome they desire. Okay, yeah, maybe I may give you an example of what a Nash equilibrium is, just to make sure that you understand what I'm talking about. So what I'm going to do, I'm going to copy here and I show you a Nash equilibrium. I'll put it here. So in this Nash equilibrium here, I just give an example now. Take an example that this is negative. That by playing strategy 2, player A brings about a loss to himself of negative 13, and this also brings about a loss of negative 10. Okay, now this is a scenario we are trying to look at. We are trying to say, okay, if I move from strategy 1-1 and I try to play, if player A chooses to play strategy 2 when player B is on strategy 1, strategy 2 will lead to a loss of 10. Okay, a loss of 10 on the side of player A. Okay, and player B will only gain 4. Okay, and if player B chooses to play strategy 2, whereas player A is on strategy 1, it will lead to a loss of 13 on the side of player B. whereas player A will now be able to gain only 1 instead of the original 5 when they're both playing strategy 1, strategy 1. Again, if they both play strategy 2, you see the gains they are getting 7, 7. But if one, just a minute, if this is reduce them to 4, yeah, this will make sense. Okay, so if this one is 7, 4, that means that it is not palatable, it's not attractive. It's not attractive because if this one plays strategy 2 and this one plays strategy 2, okay, this means that the gain will only be 4. Whereas if they play strategy 1, 1, the gain will be 5 on the side of A and 9 on the side of B. Here it is 7, 4. So in other words, there are other possible strategies, 3 extra possible strategies, but strategy 1 is the most preferred strategy, okay, because the other strategies will lead to a decline in the current position of value, okay, compared to the other values. So in other words, if you move to 1, 2, you get this particular payoff, which is below, very much lower compared to this one. And it's even detrimental on the side of A. If you move to this particular strategy of 2, 1, it will affect B significantly, negatively. If you go to strategy of 2, 2, it is also positive, but it is lower than 1, 1 in terms of payoffs. So because of such a situation, therefore, strategy 1, 1 is considered to be the Nash equilibrium. The Nash equilibrium. So if I want to write here, therefore, I will consider this one to be the Nash equilibrium here. Nash equilibrium. Nash equilibrium, because it's a kind of strategy, it's a kind of payoff, okay, based on strategy 1, in such a way that both players are not willing to change to any other strategy. Okay, so Nash equilibrium is a decision-making theorem within game theory that states a player can achieve the desired outcome by not deviating from their initial strategy. Not deviating. So initial strategy is 1, 1, and they're not willing to deviate from that particular strategy because it gives them the maximum possible gains. And any other strategy will lead them to a loss they didn't plan to get. Alright, so that is what we call the Nash equilibrium. Then we talked about minimax principle and max-min principle. We talked about it earlier. Okay, now let's discuss the common scenarios. The common scenarios that exist in game theory, okay, that we need to understand. Okay, and by understanding these common scenarios, we shall be able to give us a picture of this thing called game theory in terms of payoffs and other things. The first scenario is what we call the prisoner's dilemma. Okay, and maybe you may get some time and maybe read more about it if you get some chance. Okay, and right. So what I was trying to explain to you is that common scenarios used. The first is prisoner's dilemma, and this prisoner's dilemma is also a game of its own kind, and it's a very common game in the sense that it is used mainly to explain decision-making process amongst people. Now you have prisoner 1 and prisoner 2. These prisoners are in such a way that they committed a very serious offense, and in that serious offense they were given a punishment, and this punishment is what you see here. Let me try to shade it a bit. Let me see, where are you? Yes, here you are. I'm going to shade this one as a beginning position. That's the beginning position, okay, whereby they had 2, 2. That's the position they had, 2, 2, in the sense that the crime they committed, okay, they were given 2 years each. 2 years each to go to prison and they get out. But now, out of curiosity, policemen came and found out they actually had good reasons to believe that these people who were caught and now in prison are the ones who were causing mayhem in the near past. Okay, so they wanted to find out if they can be able to give them a deal. Okay, so they were put in separate rooms. After being put in separate rooms, they were given a chance to confess or deny. They were given a chance to confess or deny. Okay, so they were told. The police officer went to prisoner 1 and told him, okay, if you confess, we shall give you only 1 year. Okay, 1 year in prison. Okay, if you confess, we'll give you only 1 year in prison. Okay, and your colleague, if he denies, we shall give the person 10 years. But if you both confess, each of you shall be given 3 years. So you can see here, if they both confess, they shall be given 3 years. In other words, 1 year in addition to the original 2 years they had. But if one confesses, another one denies the new accusations, okay, that means the person who confesses will get only 1 year. That is a benefit, okay, because they originally have 2 years, okay. But of course, the person who denies will be given 10 years. That is for prisoner 2. And if prisoner 1 also denies, will be getting 10 years. 10 years, whereas the colleague will be getting 1 year. Now, this is where the challenge is. The challenge is that of the two prisoners, they don't know each other, okay? They don't know each other, and they are in separate rooms, so they can't even negotiate to see what they're supposed to do, okay? Because if they both deny, they maintain the current position they are in. You can see payoff of denying, both of denying, is the current position of 2 years, 2 years, okay? Now, this is the situation we're in, therefore. The situation is that what would a prisoner do? Now, because they don't trust each other, that's the issue of trust that comes in. Because they don't trust each other, okay, they would say, okay, if I deny, I get 10 years. But my colleague may also deny, right? So if I deny and my colleague denies, we shall all get 2 years each. But what if my colleague does not deny? I deny and my colleague confesses and implicates me. That simply means that I will get 10 years and my colleague will get 1 year. So this is the thinking in each of the prisoner's head. Therefore, because of that, the only option they are left with, which is a very juicy option, is to confess. Okay, because they are not very sure. Okay, because if he confesses, there are two possibilities. If prisoner 1 confesses, there are two possibilities: either to get 3 years or to get 1 year, depending on what the other person will do. If the other person also confesses, they both get 3 years. If the person denies, the player 1 also gets only 1 year, and player 2 gets 10 years. The same reasoning is now in the head of prisoner 2. He also says, I think it is better I confess, because if I confess, I'll either get to the 3 years or 1 year, depending on what prisoner 1 will do. Okay, so because of that, therefore, they both confess. That's the most probable position. They both confess, and they all end up with what? With 3 years. Now, these are two possible Nash equilibriums, but the most accepted position is this sort of confessing and confessing, because they don't know what the other person is doing. And besides that, it is better because when they confess, there's a possibility of only getting 3 years or 1 year. Okay. The other, of course, the opponent will get 10 years, and nobody wants to get 10 years. So, because of that, therefore, they both confess and they get 3 years. Okay, 3 years in addition to the 2 years. Okay, to make it so 1 year in addition to the 2 years to get out of 3 years. So, that's another example of a Nash equilibrium. Okay, whereby the other possibilities, but these other possibilities are not attractive. Okay, so just take the most attractive possibility, though it also has its own penalty, but the penalty is not as high as the other possibilities that you could have taken. Okay, so that's what we call prisoner's dilemma. A similar case exists with the battle of sexes, whereby one husband and one wife. Okay, they love each other so much, and they want to be with each other so much. Okay, but there's this kind of scenario. But every weekend there is either a kickboxing show or a ballet show. Now, a wife loves the ballet show, and the husband loves the kickboxing show. Now, if each goes to their own show, they won't enjoy because they need the company of each other. That's why you can see here, if the husband goes for kickboxing and the wife goes for ballet, the payoff is 0-0 because they don't enjoy being away from each other. Okay, they don't enjoy being away from each other. The same applies to if the husband goes for ballet to help make the wife happy, and the wife goes for kickboxing to make the husband happy, and they so end up that they are on different places at the same time. They will again not be happy. Okay, they won't be happy because their happiness is based on them being together. Okay, now this is another scenario of Nash equilibrium. So they end up agreeing that maybe this weekend we'll go for kickboxing, and if that happens, this will be the payoff. In such a way that the husband will benefit more because he's watching what he likes, but at the same time he's with the wife. Then maybe the next weekend they can agree to go for ballet. Okay, both of them. In this case, the wife would be more happy, okay, because she's watching what she likes, but at the same time she's with the husband. So that togetherness is 1, and additional happiness of 1 make 2. And that's another example of a Nash equilibrium, or another example of what we call game theory and the payoff matrix. Okay. Then we have another one called the free riders problem. Free riders problem. In this free riders problem, we're talking about common goods, which include such things such as water, health, services offered by government, and things of that nature. In this free rider problem, we see that there are 2 possible strategies participants can have. Either you defect or you cooperate. What I mean here is that when you have a common good, you can decide to cooperate with each other in the process of utilizing that common good, so that the common good benefits everybody. Okay? Now, there's a possibility that someone can decide not to cooperate, and therefore they defect from cooperation. Okay? Now, we're trying to say that if they both defect, then there will be war. In other words, if they both defect, they will start grabbing the resources. They want to have them alone. Okay? So in the process of grabbing the resources, they want to grab them alone and be able to enjoy themselves without without minding what the other person will have at the end of the day. Therefore, the other person will also feel bad. They're also trying to react. They will react. So if they both react, that automatically results into what we call war, or to call the survival of the fittest. Now, this is the most undesirable situation in the game theory. Okay, and that's why we say, okay, why don't we decide to cooperate? The most desirable position is here. They both cooperate and they both enjoy the resources. Okay, but if one cooperates and one defects, automatically the one who defects will gain it all. Okay, and the one who cooperates will lose, and that is a very bad situation. That's another example of what we call the free rider problem, because the people who are free riders, they want to enjoy, they don't want to work. Okay, so they are good at defecting, they don't like cooperating. Okay, so that's what we call a free riders problem in game theory, and it is also another very practical situation in our lives today. Okay, and it can be solved using game theory. We simply have to take a strategy whereby everybody takes responsibility and we cooperate in utilizing the common goods. And in that process, we shall be in position to be able to enjoy the common goods together. Okay. Now, enough of the stories. Let's go to computations. So the first computation, we're trying to say, before we go to the computation, we're trying to understand what is the main focus of this computation. As I explained to you earlier, in this particular situation here, just a matter of recap, when you look at payoffs, we have this scenario whereby both players indicate their payoffs, but because, as I indicated to you, is that in the process of solving for game theory, okay, getting solutions in game theory, our main focus is to ensure that we take a position of one of the players, and the one of the players we are interested in is a player who is in the horizontal sector or section in a payoff matrix. In this case, it is the row section of the player B. So in other words, we shall take position of player B, and if you take player B's position, then we shall ignore the pairs of player A, and therefore we shall take 9, 13, 4, and 7 relating to player B, and we place them in our new matrix, and these will be gains for player B and losses to player A. Okay, so that's the first thing, and I told you that this is what we call a zero-sum game, and because there are 2 players, we call it a 2-player zero-sum game. Okay, now we are going to use the same principle when you're doing the computation here in the game theory. That's why we say the focus is on 2 persons zero-sum game theory. Zero-sum game theory is a game in which a gain by one player becomes a loss to another player. We talked about this one earlier. The computation focus determines whether the players should use mixed or pure strategy. I talked to you about strategies earlier, and I told you there are 2 possible strategies that someone can use in the game theory. One is a pure strategy, another is a mixed strategy. And the mixed strategy is whereby more than one strategy is used. When more than one strategy is used in a game. Now, when more than one strategy is used in a game, that means the probability of which of the strategies used is less than 1, and therefore you add all of them, you get only 1. But there's a possibility of having pure strategy. And in pure strategy, only one strategy is used. Even if there are 5 displayed in the question, you may realize that only 1 is used. Okay, and that one strategy will have the probability of 1. Okay. Now, After knowing that, you have to go ahead and compute the overall value of the game, which I told you, it is the maximum possible payoff, okay, which is a gain to the player of focus and a loss to the opponent in the game, as I told you earlier. Now, what are the steps? The steps are here. I'm going to show you. We're going to look at the steps which we shall follow when we are looking at game theory computation. Okay. So as we begin our computation, start. You determine the existence of saddle point. That's the first thing you're supposed to do by using a minimax maximin principle, as I'm going to show you in the next question I'm going to do for you. Okay. So determine the saddle point. So the question is, does the saddle point exist? If the answer is yes, compute saddle point. Okay. Of course, when we talk of saddle point, that means there's a pure strategy as well. So compute the pure strategy probability, which most times it is 1, okay, and determine the value of the game, and automatically you stop. Okay. But what if the saddle point does not exist? You ask yourself another question. Does dominant principle apply? A dominant principle is another technique we're going to look at when you're looking at game theory. Okay. And this dominant principle just simply explain that there are some strategies which are dominant to others. But that is something that we shall have to determine based on the computations we are going to do. Now, if the dominant principle exists, then we are told that use it to simplify the matrix and compute probabilities. And automatically after doing that, you stop. But what if the dominant principle does not exist? If it doesn't exist, therefore, you go to the next phase, is determine the probability of the mixed strategy. What does this mean, therefore? When you have saddle point, then you have pure strategy. If you don't have saddle point, then you can use dominant principle to find if there's a possibility of getting saddle point. And even if you do some dominant strategy and if you don't get saddle point, that's not the end of the story. You must be able to use the available information to compute the probabilities, and these probabilities lead you to having what we call a mixed strategy. We are going to look at a question and see how this thing can be done. Okay. After computing the probabilities, then automatically you end up by what? By stopping the computation. Now, with this particular procedure, it's a flow chart. Okay, you start from here. Okay, you move down, down, down up to there. So what we are going to do now is to look at a question and see how this particular procedure I've just displayed here for you works. Okay. Now let's move down. This is the question here. We are told that DFCU and Standard banks are growing rivals in the banking sector. They all want dominance in the industry. In order to realize this, they consider applying 3 key strategies: loan interest incentives, customer control of account through automation, that is CCA, and general mobile banking services, GMM. The strategies were applied in order to capture a group of customers. There are 40 customers that they are competing for. These strategies have the following payers for the banks based on the number of customers tapped by each bank. So now the question provides you with the payoffs, as I told you before. These are the payoffs. Okay, and the beauty about this is that both banks are using the same strategies. Okay, but automatically, because of the difference in resources, the same strategy may have different payoffs depending on which bank is using the strategy. So question number 1. Consider that you are a staff of DFCU, in this case this DFCU here, okay? What would you recommend to be a strategy? What would you recommend to be a strategy or strategy that the bank should take? That's the first question. And based on your answer in the one above, what would be the corresponding strategy for Stanbic Bank? Now take the position of a staff of Stanbic Bank. Does your answer in A still hold, and why? And based on your answer in C above, what would be the corresponding strategy for DFCU Bank? And explain your answer. Now this is a direct question and you're going to go through it together. I'm going to provide a solution here. Okay. Solution. So we're going to start with part A. It says, considering your staff for DFCU Bank, what would you recommend to be a strategy or strategies that the bank should take? Now, what you're going to do now, I'm just going to copy this question here, okay, and I paste it down here, okay, like that, okay, like that. Now, here, what we want is to find out, I've already been told I should take the position of a DFCU bank. In this case, if I take the position of DFCU bank, that means I ignore the payoffs of the other bank. I just focus on the gains of DFCU Bank and the losses of Stanbic Bank. So these are 40 customers I'm talking about. You see that these payoffs are all totaling to 40. 12 plus 28 is 40, 40 plus 0 is 40, 19 plus 21 is 40, 20 plus 20 is 40, 25 plus 15 is 40, the rest are also 40, 40, 40. That means therefore the gains of DFCU Bank and the losses of Stanbic Bank in terms of number of customers. So what I'm going to do, I'm going to remove all these payoffs of Stanbic Bank, okay, the payoffs here. I'm going to remove them, okay, so that I remove the payoffs of only DFCU and I consider them in my matrix computations, okay. So I've removed those ones. After doing that, remove this one as well, okay. Okay, so now let me do this just to center them like before. What has happened now? Let me see. Okay, so I think there's a problem here. It's this one. Okay, that's it. There we go. So now I'm interested in DFCU winning, and before I proceed, I told you the procedure is first and foremost is determine the existence of saddle point, and we shall do that by using what we call the minimax principle. The minimax principle. So we're going to determine first and foremost the row minimums. Okay, then we shall do determine the column maximums. Okay, then we shall maximize the minimum values and minimize the maximum values, because the losses must be minimized and the gains must be maximized. So I will add here a column, 2 of them like that. Okay, so merge this and merge this one as well. So we shall say row minimum. In the first row we have, just a minute, just put this one in the middle. Okay, the first row the minimum value is 12, the second row the minimum value is 22, and the third row the minimum value is 15. Okay, so we shall now get what we call maximin value. Okay, maximin value will be the maximum value of the minimum values. So the maximum value is computed from these 3. So you get the maximum value of the row minimums. The maximum value of row minimums here is 22. So I'll put here 22. All together. Now I do the same for the columns. So I will add there. Okay. All right. Here we go. Okay. Shall I put this one as black? I don't want that one to exist. Okay. So what we're going to do, shall do the same thing. I just want you to see it properly. So layout, do this one. So layout. So we shall say column maximum. Then we shall put here minimax value. You know that the minimum value of the maximum, value of the maximum totals, okay, maximum totals. So we shall set what's the maximum value in the first column. 35, 20, 12 is 35 here. This is 40, 25, 20. The maximum value is 40. Here, 19, 22, 15. The maximum value here is 20, 22. This is supposed to be black. also supposed to be considered there. Okay. Now from there we see what is the minimum value or the maximum possible losses. So these are possible losses. These are possible losses here. Okay, but what is the minimum value of the maximum possible losses? 35, 40, 22. The minimum is 22. So as you can see, the minimax value is 22. The maximum mini value is 22. Okay, from the column point of view and from the row point of view. Okay. Now, what does this mean therefore? It means that this particular game has a saddle point. Okay, and if it has a saddle point, therefore our situation is actually sorted out. Okay. Remember what we said earlier in our discussion here up here, we said that let me just show you as a recap. See here? A saddle point is a point in a game theory whereby a minimax value is the same as the max-min value. This point is also referred to as the value of the game. We shall discuss more about this when computing the game theory, and that's what we are doing right now. Okay, so now let's go back down. Let's go back down here. Yes, so we see that this is the place we computed the row minimum. So let me share, to avoid confusion, let me share this part here. Okay, and then we saw this is the column maximum, so I share that part as well. Okay, then we have this section of minimum value. Okay, so you can give it that one. Also this is the maximum value, give the same. So we see that one now, which means we started with these 6 positions here, 9 positions. Now we see that the minimax value is here, and I'm going to shade it red. What does this mean therefore? I'm going to interpret this one further. So it means that the game has a saddle point. Okay, with value of 22. Okay, that's the most important thing. The first thing you need to notice here, the saddle point of value 22. Okay, this means that the value of the game, if I can be able to squeeze this a bit, probably, so it can fit here. It can't fit. Right, I'll just push it down. The value of the game, is 22. Value of the game is 22. This further means that 22 customers is the maximum possible gain, okay, that DFCU bank can have. Maximum possible gain that DFCU bank can have, okay, regardless of the strategy that Stanbic Bank may use. Okay, that's how you interpret it. It's the maximum possible gain, okay, that DFCU Bank can have regardless of the strategy that Stanbic Bank may use. Okay, so we should also go to saying that the results of the game indicate that there is an existence of a pure strategy for both banks. Okay. Let's put it this way. DFCU should use the strategy of here we shall say CCA. CCA based on our question, CCA is, if you look at the question, it is customer control of account through automation. Because CCA is where the saddle point is, it is here. So to achieve the 22, it must use CCA. Customer control of account through automation. Let me just copy it here. Customer control of account through automation. That's what DFCU should use. Okay, to realize that particular game. So DFCU should use the strategy of NAT. Okay. This is a pure strategy. This is a pure strategy for DFCU bank with probability of 1. Okay. The other strategies have probabilities of 0. Probabilities of 0 because they shall not be considered. 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 Okay. These strategies are. We have LII and GMM. LII and GMM. Okay. Similarly, we shall say Stanbic Bank. Okay, let me just copy this one and edit. Okay. Copy and edit this one. So Stanbic Bank here. Should use which strategy? Should use the GMM strategy. What's the GMM strategy? GMM is the General Mobile Banking Services. General Mobile Banking what? Services. General Mobile Banking Services. Like that. This is a pure strategy for DFCU bank with the probability of 1. The other strategies have probabilities of 0 because shall not be considered. These strategies are CCA and LII. So you can see now, in Stanbic Bank we'll be having the GMM strategy, and DFCU bank will be having a CCA strategy. In this case, Stanbic Bank will have the minimum loss of 22 customers, and DFCU will have a maximum gain of 22 customers, and the game will have ended. The overall value of the game will be 22. Okay, so that is how you conclude this particular section. Okay, all right. Let me see if there's a. Yeah, that's okay. Okay, so that is how you end that particular section, and we have answered this particular question. Based on your answer in A above, what will be the corresponding strategy for Stanbic Bank? We have already mentioned that will be the GMM. For DFC will be CCA. Okay. Now take the position of staff of the Stanbic Bank. Okay, this is very good. So we are going to repeat this particular scenario. Okay. But this time round, we are going to take a position of Stanbic Bank because we want Stanbic Bank to win. Stanbic Bank to win. Okay, we want Stanbic Bank to win. Now, what we are going to do is we are going to capture this particular question. Okay, and then place it here. Okay, so we see that Stanbic Bank must come here. But before that, let's first remove all these payoffs. Okay, then we shall do a transpose. We shall do a transpose, and then that transpose will help us. The transpose will help us to remove, to adjust this particular game, okay, to fit the requirements of a winning strategy. Okay. Delete remain with this one. This one. Five. So at this particular point, we are going to do what we call transpose of a matrix, so that we can have Stanbic properly reflected where it is supposed to be reflected. So as you can see here, this is our new matrix, but of course I've changed the names. This becomes Stanbic, because that's the way we're supposed to place it. Stanbic. There's a winning team, and DFC this time is the it is not what we consider to be the losing team, DFCU, because our game now has changed. We want Stanbic Bank to be the winning team. Okay, so the procedure is the same. First, look for the existence of starter point. So we are going to look for existence of starter point. Okay, we shall also do the same down here. Okay. Now this is what we call row minimum. This one shall all put it black. I don't want it there. Okay, that's all black. Then here shall have the other value, max min value. Row minimum. Then have your column maximum. Column maximum. Okay, then here shall have a minimax value. Okay. Correct. This one also be the same here. Correct. So we shall now pick the row minimums. Okay. Number one, the first minimum value of that particular row is 5. The second here is 0, and the next here is what is this? 25, 20, 21 is 20. So maximum value of the minimum items. Maximum of the minimum value is 20. Okay. All right. Next we shall have here maximum value is 25. Next maximum value is 20. 20. Oh, hold on. It's supposed to be 18 here. So, sorry about this. 18. The number is 18 here. This one is 18. Okay, so we have 5, 8, and 18. Then next we have 35, maximum value. Maximum value here is 20, the maximum value is 28. So again, we do the same as before. We shall find the minimum value of the maximum items. The minimum value of the maximum item here is 20. Okay, now since maximin value is not equal to mini max value, not equal to mini max value, there is no saddle point. There is no saddle point. Okay. Similarly, there is no pure strategy. now there's no pure what? There's no pure strategy, because now we're going to go for mixed strategies. Okay, so like before, we're going to shade this one, okay, to differentiate it from the others. Okay. Okay, so we have this one as well. Okay, so now this is the position we are in. The minimax value and max min value are the same. Because of that, there is no saddle point, and because there is no saddle point, we shall not say we have pure strategy. Instead, we are going now to look for a possibility of having mixed strategy, a mixed strategy. So how do we go about this? I'm going to show you a few minutes from now. I'm going to show you how to deal with this particular scenario whereby we don't have a saddle point. Okay. And this is Stanbic Bank. DFC Bank was straightforward, but now Stanbic Bank requires more than one strategy to win, because there's no possibility of having saddle point. Okay, so now let's go and compute these other strategies. Okay, but now before we compute, let me remind you of what we discussed earlier. We said that in this particular flowchart, that determine the existence of saddle point, which you have done by using minimax principle. And ask yourself, does saddle point exist? If it exists, compute and end. That's what we did before. But now we have realized it does not exist. So the next step is to ask ourselves, does the dominant principle apply? Does the dominant principle apply? So that's the next question we're going to ask ourselves. Does the dominant principle apply? Okay. So we're going to use the same matrix we did before. Okay. And then we're going to compute that particular scenario we are trying to refer to. Okay, so we are going to pick this. Let's pick everything. We shall remove after. Copy, and we paste it. So we paste it here. Okay, we paste it here. This is the scenario we have. So we are going to remove all these columns which are shaded, because we don't need them in our computation. We are going to put others in the process. Okay, so we shall start from here. So what is this now? I'm now removing the rows, okay, because I don't need them right now. So this is where we were before. Okay, so now the first thing you're supposed to do is to check if there's a dominant strategy. Check if there's a dominant strategy. There, what you're going to do now is to get the totals of each one, of each item here. So as before, we are going to add the rows and columns. Again, we use this particular knowledge to get the totals, which you can compare with. Calculate each other and be able to know where to focus on. So take an example like here. Total of the three is 28 plus 20, that is 48. 48 plus 5 is 53. 28 plus 50, sorry, 20 plus 15 is 35. And 25 plus 18 plus 21, that is 46. 56 plus 8 is 50. 25 plus 18, sorry, plus 21 is 46. 56 plus 8, it is 64. 64. So you write here 64. Okay, so we are going to begin with this section of rows first. Then we shall go So what I'm going to do here is to pick out the highest figure is 64. Total of rows, the highest figure is 64. And then I compare it with the next row to find out if the dominant principle applies. So if you look at 25 and 20, 25 is bigger. 18 and 15, 18 is bigger. 21 and 0, 21 is bigger, which means this strategy of L11 is dominant to this particular strategy, and therefore we shall strike through that particular strategy because it does not add value. Are we together there? So remove this one. I'm going to put it in red, or maybe just use the strike through, and there we go. We have removed that particular section. Then from there you compare again the two rows remaining. 25 and 5, 25 is bigger. 18 and 20, 18 is smaller. 21 and 28, 21 is smaller. So it means for the strategy LII and GMM, the dominant strategy does not exist. Now that we have finished dealing with the rows, now we go to the column. And again we add the remaining components, okay? We add the remaining components. This is 30. 25 plus 5 is 30. 18 plus 28 is 38. Then 28 plus 21 is 47. Okay? Sorry, 49, not 47, 49. 8 plus 1 is 9, 2 plus 2 is 4. Now, again, the highest figure is 49 in terms of total, which means we expect GM strategy to be dominant strategy, but we shall compare it with the other strategies and see what's actually dominant or not. So with the first strategy, we see 28 and 5, 28 is bigger, so that's okay. 21 and 25, 25 is bigger, so it's not dominant to LII. Let's see if it is dominant to CCA. 28 and 20, 28 is bigger. 21 and 18, 21 is bigger, which means therefore, for GMM is dominant to CAA. But unlike the rows whereby you subtract the row with the you cancel out the row with the smallest figures. In columns we shall cancel the column with the highest number of figures. In this case it is 49, and this 49 is dominant to what? It's dominant to CAA, so we shall cancel this one as well. So this one should go. So now we are remaining with 4 items. We shall write them here to show you what is actually remaining. I'm going to copy this one and I write my strategies down here. So I'm also going to show you what I've removed. So shall I remove this particular row? Just come here and remove it. Okay, and this column here, come and remove it. Okay, so now let us remove this one as well. Just a minute. So I'm going to. This should also go. This one here. This should also go. So yeah, that's it. Then finally we have this one. It also goes. And this is the possibilities we are remaining with after cancelling out. Okay, so we have cancelled out the GMM, we have cancelled out the CAA, we removed the LII plus the CCA. So of course CCA has gone also, it has also disappeared, it's no longer part of us because we have deleted it. So now we're remaining with LII and GMM on the side of Stanbic Bank, and on the side of DFCU Bank, let me add it there. DFCU Bank, we're remaining with something else. In DFCU Bank, we're remaining with LII and CCA. So you can see the common strategy for both banks and whatever, and yeah, the both banks is what? Is LII. LII. Okay, let me see, where are you? Okay, let's do it this way. So what you're going to do now is to compute what we call the payoff. So the payoff matrix is there, but now we're going to compute the oddments, and from oddments we're going to compute the probabilities, okay, for each of these particular strategies. And then from there we shall make our conclusion, and we shall also produce what we call the value of the business that shall be considered, okay, value of the business that shall be considered, okay. Now so we shall have this one here. Okay. Remember what we have just done by removing the rows and columns. We have applied what we call a dominant strategy. The dominant strategy. Okay. The dominant strategy whereby you're removing the rows and columns that are dominant, okay, to the others, and remain with the others which are what? Which are not what? Dominant, okay? Yeah. For the case of row, you remove the rows which are low, in terms of the ones that are dominated, you remove them, and for the case of column, you remove the columns that are what? Are dominant. Because in terms of the case of the columns, we're trying to minimize the maximum losses, and in the case of rows, we're trying to maximize the possible minimums, okay? Yeah, so that's the reason behind it. Okay, so now we have these figures. So I told you we're going to compute the oddments. We have what we call oddments, and from there we shall get probabilities. Again, shall have this one as black. The same applies to this one as black, and this one as black. Okay, so we just need the remaining part. So again, here we shall have to do the oddments as I told you earlier. I'm going to do this match. Okay, so we shall have here oddments from the column side point of view, and we shall have here probabilities. Now, how do you compute the oddments? How do you compute the oddments? You compute the oddments by subtracting. So I shall say the difference in 20 and 5 is what we call 15. But now this difference you get here, you write it down. You write it down in the LII column. So I shall put here 15 as the oddments. As a result of difference between 20 and 5. The difference between 25 and 18 is 7. We put it up here. The same applies to the column. 25 and 5, the difference is 20. You put it on the other column. Difference between 20 and 18, the difference is 2. You put it in this other column. Okay. Now the total for both 2 plus 20 is 22. 17 plus 5, sorry, 7 plus 15 is also 22. So the common total is 22. Okay. Now, let me first shade this part here to show that these are just additional columns and rows. So we shall have that one and also have that one. These are the oddments. Then we shall have the probabilities here. The probabilities there. Okay. So the probabilities there. Okay. Now, so we shall say, okay. Now, the probability for GMM will be 7 divided by the total. Actually, this total must be given a stronger color to make it different. Yeah, that's okay. So we shall have here, it is 7 divided by the total, which is 15. This, sorry, 22, not 15, 22. The same applies to this one, it will be 15 divided by 22, that's the probability. 22 is this one here, so 7 divided by 22, 15 divided by 22. The same applies to this one here, will be 2 divided by 22, and this will be 20 divided by 22. 20 divided by 22. And that gives us the probabilities for each of the strategies that these two banks may take. Okay. Now we shall conclude by saying that, okay, based on the computation above, written above. 1. Okay, 1 that Stanbic Bank will have to use a mixed strategy approach. Mixed strategy approach by combining the LII strategy, okay, and the GMM strategy. Okay, so shall I say more reliance should be given to the LII strategy in order to maximize minimum possible gains in the game. Okay, this is because the LII strategy has a higher probability as compared to GMM. Okay, high probability as compared to GMM. All right. Again, we shall say DFCU Bank should use a mixed strategy, okay, approach to minimize maximum possible losses, okay, in the game. To do this, the LII strategy should be used alongside the CCA strategy. More reliance should be put on the CCA strategy. More reliance should be put on the CCA strategy, okay, since it has a higher probability. Okay, yeah, since it has a higher probability. So that is what we expected to do, since it has a higher probability. Okay, now the last thing you're supposed to do is to compute the value of the game. Okay, shall say therefore the value of the game shall be computed by using the formula below. So shall say okay, so let me put a small equation here. Okay, so value equals to payoff matrix value, okay, payoff matrix value times times oddment, okay, times oddment, okay, divided by total of oddments, total of oddments, okay. So this should be I, okay, and this should be I, and this should be summation. So we're going to insert a simple summation of this, okay. So this is what you're going to compute. You're going to compute summation of the payoff matrix value times its corresponding oddment value, okay, its corresponding oddment value, okay, divided by total oddments, okay, for each, for any row or column, okay. This should be for any row or column, whichever row or column is used, the same outcome is obtained. Okay, so let's try that on C. So in our case here, we shall have the first row, we have 5 and 20 as the payoff matrices. These ones here, 5 and 20 for GMM, and the oddments are 2 and 20. So let's find out what we get. Divided by 22, of course. So we shall get, shall say, using row with strategy, what do we start? Which strategy is GMM? With strategy GMM, we shall have the following. So shall say it is 5 here times 2 plus 20 times 20, okay. So it shall be open brackets 5 times 2, okay, plus 20 times 20. Okay, everything divided by 22, which is the total oddments, okay. This should give us the final answer, which is 5 times 2 is 10, 20 times 20 is 400, so it is 410 divided by 22, which automatically, if you do the you can do the computation later on, but I'm just going to show you that this thing this is how it is done. So we are going to use other strategies, okay, and we see if we get the same answer. So if you have to use, let's say, strategy with the LII, so use row with strategy LII and see what we get. LII, we shall have 25 times 2 plus 18 times 20. So we shall have here 25 times 2 plus 18 times 20. Now, divided by 22. Again, if you have to do this mathematics very well, 25 times 2 is 50, 18 times 2 is 36, 36 plus times 10 is 360, 360 plus 50 is again 410, okay. So you can now try in your own free time, okay, try to do the same computation using columns. The logic is the same. You get the payoff matrix value multiplied by the oddment value corresponding ornament value. So in case of columns here, we shall have 5 times 7 plus 25 times 15 and divide by everything by 22. We should be able to get the same answer, which is 410 out of 22. Okay. Now, what does this 410 out of 22 mean? It means this is the maximum possible value that Stanbic Bank can gain in terms of number of customers. Okay. By applying a mix of LII strategy and GMM strategy. Okay. Now, if I were to use a calculator here, we shall see that 410 divided by 22 is equal to 18.636, which is roughly 19. But if you're talking about number of customers, so you are supposed to use a discrete value, which is 18. Therefore, we shall say based on the output, of the value of the game, okay, the maximum number of customers that Stanbic Bank can be able to gain by applying the mixed strategy is 18. That's the value of the game. Because now we are using the discrete value 18.6. You can't say 19 because you can't have half a human being. Okay, so we shall say it is 18. All right. Now this becomes our final position. Okay, as far as the Stanbic Bank is concerned. Okay, and as you can see, the strategy for DFC also has changed. Previously, DFCU, when our focus was on DFCU, we had a pure strategy. But now, when our focus changed to Stanbic Bank, we no longer have a pure strategy. Okay. Instead, DFCU will be losing 18 customers to Stanbic Bank if we had to use a mix of LII and GM strategy on the side of Stanbic Bank and LII and CCA strategies on the side of DFCU Bank. So this is how we compute the different oddments and probabilities. Okay, at the end of the day, we get the value of the game and we suggest to the different players on their possible payoffs and the maximum possible gain or loss given the situation in the game. Okay, given the situation in the game. So maybe I have shown you how to go through this game theory using this particular flow chart. Okay, starting from start, determine the saddle point. If it is there, you will do it like we did the first example of DFCU Bank. Now in the second example of DFCU Bank with Stanbic Bank, whereby where now our focus is on Stanbic Bank, we realize there's no saddle point. We ask ourselves, is there a dominant strategy? Lucky enough, we found there was a dominant strategy and we used it by reducing the rows and columns, and we got a smaller matrix. Okay, as we saw here. We use the dominant strategy by knocking off. Where is it? It is here. Yeah, it is here. So this is cancelled because it was a minimum. It is not a dominant strategy, so it is dominated by another. So this CA was removed, okay, by cancelling, and also GMM on this side of DFC Bank was also removed. So we remain with LII and CECA, GMM. Sorry about that. GMM together with what? With LII, they also remained, and we remained with those 4 possible payoffs. This one here, we remained with these possible payoffs, and these are the ones now we transferred into a smaller matrix. 5, 20, 25, 25, 18. We transferred to this smaller matrix here. You can see 5, 20, 5, 20, 25, 18, 25, 18, because these were not cancelled. Okay, and we use this one now to compute oddments and probabilities to get a mixed strategy probability. And as you can see in this particular answer, on the side of Stanbic Bank, the most preferred strategy here is automatically what we see here is it is LII, because it has a high probability of 15 out of 22. And on the side of DFC, to minimize its losses, the most preferred strategy is CCA, because there's higher probability. Okay, yeah. So basically, that's what you're supposed to do. All right. Now we have seen the different examples. Let's look at another example whereby you may not have any of these oddments, or you may not have the saddle point. You may also not have the what we call you may not have the saddle point, you may not have the dominant strategy. Okay, and we're going to look at all those things by testing. Okay, so I'm trying to show you that we can use all the positions. Starting from here, we have looked at saddle point, we have looked at dominant strategy, and now we're looking at the situation where you don't have saddle point, also you don't have the dominant strategy or principle, and you proceed this last position and you stop. Okay, that's the last example I'm going to show you in this particular situation. Okay, so I want you to look at it here. Okay, this example here. Okay, so we're told NTV and NBS are two powerful TV stations in Uganda. They are neck to neck in the process of enhancing their viewership in the country. In order to further increase their viewership, they both considered to use three important strategies: using social media, that's USM strategy, displaying regional content, that's another strategy, and displaying content that is in sync with the community around, that's CTS strategy. So the payoff matrix in terms of the number of people in thousands is displayed below. Now in this case, our focus is already determined to be on the side of NTV. We want NTV to win, okay? We want NTV to win this particular game, okay? So we're trying to say, okay, if NTV wins, okay, it will be able to gain 12, 6, 12, 14, 4, 6, and 10, 12, 12, okay? Now, whatever game NTV game X, NBS loses. So this also is an example of a zero-sum game. It's an example of a zero-sum game. So we are going to look at the zero-sum game right now, okay, and be able to answer it. What is the first question? Should there be use of pure strategy or mixed strategy? Remember what you're supposed to do? To know whether pure strategy is there or not, we're supposed to check if there is saddle point, and if there is no saddle point, there is no pure strategy. Therefore, we shall have to go ahead and find a mixed strategy by checking if there is a principle of dominance in existence, and if that principle is not there, then we go ahead to the next step of identifying how best you can solve the problem. Alright, so let's go and without wasting any more time, let's go and do this thing. So the first step, as I told you, I'm going to copy this and we test for saddle point. Okay. Okay, so shall we have solution here? Solution. Okay, so we shall post it there. Now I'm going to do those two items there like before. Okay, so we shall have here that one there, minimax, and so this is raw minimum. That's the first step, remember, raw minimum, and then here we shall have what we call maximum value. That means the maximum value of the minimum possible gains. Okay, so these four, as usual, should be colored black because we do not need them for now. Okay, so we have that layout. Okay, we have that one. Okay, so again, this one is what we call column maximum, and this shall give us minimax value, minimizing the maximum losses. Minimax value, okay? Minimax value. So this one, there we go. Right, so we look at our rows and columns and see what we have. 12, 6, 12, row minimum 6. 12, 4, 6, row minimum 4. 10, 12, 11, minimum row minimum 10. Then what is the maximum of the minimums? Is 10. Okay, let's go this other side. Maximum value in the column is 12, 14, 10 is 14. 6, 4, 12, it is 12. Okay, 12, 6, 11, again it is 12. So we say, okay, now what is the minimum value of the maximum? It's 12. As you can see here, we do not have a saddle point. We don't have the saddle point because the minimax value and the maximum value are not the same. min max value and max min value are not what? Are not the same. They're not the same. Now, at this particular point, we're trying to say, okay, now we don't have saddle point, so probably we should go and try to apply a dominant strategy. Okay, let's try to apply dominant strategy. So the first test of saddle point, she has failed. So we go to the second test, which is the existence of dominance value. So again, we copy this one. Okay, shall we go down here? Paste it there, and now we're going to test for existence of dominant strategy or dominant principle. Okay, so let me see. We shall get the totals, raw totals. Raw totals, so 12 plus 6 plus 12. This gives me, if I'm to use a calculator here, this one is 12 plus 6 plus 12, which gives me 30. So I put here 30. 6 plus 4 is 10, 10 plus 14 is 24. 10 plus 12 is 22. 22 plus 11 is 33. Okay, so let's do this. I'm going to try to put it in the center. Correct. Now, the highest value here is 33. Let's see if it is dominant with other strategies. Yes. 10 and 14, 10 is small. 4 and 12, 12 is big. 6 and 11, 11 is big. So, 2 items are dominant, 1 is not. It can't work. Look about this other side. 12 and 10, 10 is small. 6 and 12, 12 is big. 12 and 11. So you can see it is not possible to have a dominant strategy on the side of the rows. So again, dominant strategy here is failing. So I'm shading this one red to show it has failed. Okay, so again, let's try to column wise and see if there's a dominant strategy on the column side. Okay, so column totals. Trying to find out if the columns totals are what? Have an element of dominant strategy. So we shall do 12 plus 14 plus 10 gives me 36. So this one is 36 here. Okay, then we shall have 6 plus 4 plus 12, which is 22. This is 22 here. Then we shall have 12 plus 6 plus 11, which is 29. 29 is here. So the highest of all is 36. 36. So let's see if this particular column has a dominant element. 12 and 6, 12 is bigger. 14 and 4, 14 is bigger. But 10 and 12, 10 is smaller, no dominance. 12 and 12, they are the same. 14 and 6, bigger. 10 and 11, 10 is small, so no dominance. Again, here, there is no dominance. Okay? So which means now, the second principle has also failed. We started with the saddle point principle, it failed. Now we are looking at the dominance principle, it has also failed. Which means, therefore, we have to go to the third stage based on our flow chart here. I told you the flow chart is, it shows that test for saddle point. Does saddle point exist? Yes, finish. It doesn't exist, dominant principle. Does it exist? Do it, finish. If it doesn't exist, now we are here on the last part here. So we're supposed to do, when you have tested for both saddle point and dominant principle and you have failed, and therefore now go to the last point, and therefore we're going to solve this particular question. This time we're going to use what we call computation of oddments, okay, and probabilities like before, okay. But now I want you to take note of one thing. In the question I've just completed, we were able to use the dominant strategy to reduce the matrix into a 2 by 2. It was a 3 by 3. And because of that, we were able to do the oddments of a 2 by 2 matrix, like what you see here. But now, when you're using a 3 by 3 matrix on the game theory, a 3 by 3 matrix, the computation of oddments won't follow the same procedure of getting the differences. No, we shall have a different procedure, as I'm going to show you. Okay? So let me go down and show it to you right now. Okay, so here we are. We shall copy this original question since there's failed both tests, and let's solve it using oddments. Okay, so we shall now solve it using oddments. So we have this particular position. This is the original position we had. Now what you're going to do, we're going to get the differences of rows and columns, okay, one by one. Then after that, after getting the differences, all right, so we shall be able to now go ahead and do our computation and get our probabilities. Has failed to get the dominant strategy or principle. They also failed in the saddle point. Okay, so the first step we're going to do is to look at the differences between the columns. So I'm going to look at doc minus USM. The answer will be put here. Okay, so I'll shade this area to show where the answers are going to be. Also, the next column will be USM minus CTS, which I'll also shade here. Okay, to show where those. That's what we shall put. Then we shall go to columns. We shall subtract them row by row. Again, we shall put the answers there. Again, the same second subtraction shall be there. We shall also put the answers there. Then these boxes shall have nothing, so I'm going to put them as black. Okay, so shall have that particular position. Now, we begin. Doc minus USM shall be 12 minus 6, that is 6 here. 6. Okay, next is 12 minus 4, that is 10. Okay, then 10 minus 12, that is negative 2. Then here, 6 minus 12 is negative 6. Okay, 4 minus 6 is negative 2. And 12 minus 11 is 1. Then down here we have 12 minus 14. 12 minus 14 here, that is negative 2. 6 minus 4 is 2. 12 minus 6 is 6. 14 minus 4 is 4. 4 minus 12 is negative 8. And 6 minus 11 is negative 5. Okay, now from there we compute our oddments. Okay, how do we compute our oddments? We shall say, okay, we shade this one area here and use determinant, and determinant value is computed using this particular formula here. This formula is going to be used to compute the determinant value. Okay, so we shall have remaining portion of 10 minus 2, negative 2 minus 1. So the determinant value, principle formula says, if you have a 2 by 2 matrix such that it is A, B, C, D, the determinant is determined by getting A times D minus B times C, and everything is in absolute values sign, meaning that whatever answer you get out of there, whether positive or negative, shall remain positive. Okay, so we're going to use that very principle to compute our oddments up there. Okay, so we shall say, okay, if you shade this first part here, we shall remain with the 10, negative 2, negative 2, 1. 10 times 1 is 10. Negative 2 times negative 2 is 4. Okay, so 10 minus 4 gives you 6, which we have put here. Then we shade off the first here. We got this one. So for the next, we shade off this part here to get the oddment of the middle row. We remember this is 6, negative 6, negative 2, 1. So 6 times 6 times 1 is 6. Then negative 2 times negative 6 is negative, so it's positive 12. So 6 minus 12 is negative 6 minus 12 is negative 6. Is negative 6. Alright? But because the oddment, the oddments are supposed to have the absolute value, whatever answer you get out of it shall remain positive, as what we said earlier. So shall put this one as 6. Okay. Then for the last row, we shade it as well. We remain with the 4 items up there. So we have 6 and negative 2. That gives you negative 12, and 10 and 6 gives you negative 60. So negative 60 minus 12 is negative 48. Or you can say negative 12 minus negative 60 is positive 48. So the answer here is 48. Okay? Alright, now we go down and do the same logic. We shall say, okay, for the first column here, we remain with 2, negative 5, negative 8, 6. So 2 times 5 is negative 10. 8 times 6 is negative 48. So we shall say, okay, negative 10 minus 48, negative 10 minus 48, minus 48, so it becomes 48 minus 10, which is 38. 38, so 38 comes here. Okay, so now when you shade the middle column, we shall say now remaining negative 2, negative 5, 4, 6. So negative 2, negative 5 gives you negative 10 if you multiply them. So the positive 10, negative times negative is positive. So it's positive 10. Then 4 times 6 is 24. So 24 plus 24 subtracted from 10, we get negative 14, which becomes positive 14. Because there's an absolute value symbol. Then the last item here is the column there. We shall have negative 2 and 2, 4 and negative 8. Okay, so we have negative 2 times negative 8, which gives you negative 6. Sorry, positive 16. Then 4 and 2 gives you 6. Sorry, 8. Negative 2 times negative 8 is negative 16. Positive 16 and minus 8, it gave you 8. The answer here is 8. Now, the beauty about this is that when you add the oddments, they should get the same total. Okay, so when you add the oddments, you should get the same what? The same total, which will be put here. 6 plus 6 plus 48. If we use the calculator here, we shall have 6 plus 6 plus 48. It gives you 60. So put the 60 here. Now let's do the other side. We shall say, okay, 38 plus 14 plus 8 will give you 60 again. Okay, so now that we've got the 60, now we can compute. These are the probabilities, of course. So these are probabilities. These are oddments, not probabilities, but oddments. So I'm going to put that golden color. There we go, golden color. These are all related, so we have something like that. And now we're going to compute probabilities. Probabilities will be for each section. So we're going to shade off this one as black. We don't need this part here, so shade it as black. Also this one we're going to shade it as black. So we shall have this one. Okay, so we shall say 6 divided by 60. We get probability of 6 out of 60, which is the same as probability of 1 out of 10. That's if you want to write it that way. Okay, so you can leave it the way it is. The same applies to the second item, which will be the same. So let's copy and paste. This last one shall be 48 out of 60. 48 out of 60. And that one you can leave the way it is, it's okay. When you come down to probabilities, these ones here, we have 38 out of 60. 38 out of 60. And then we shall have 14 out of 60. And lastly, we shall have 8 out of 60. Okay, so those are the probabilities. We have computed probabilities very, very well. So we have that item. Let me use a different color here. Yeah, that's fine. So to show the probabilities that have been computed already. So now we have got to probabilities, and it's very clear that NTV Uganda should use all the 3 probabilities, but the most probable probability is DOC. Okay, that's a dominant probability, so a strategy for NTV Uganda. Because it has the highest probability. Okay, and DOC means what? DOC means displaying original content. Okay, now for the case of NBS, the highest probability is reported to be under again DOC. You can see it's at 8 out of 60. It's again DOC. Okay, so again both of them must are going to use all the 3 strategies, but they'll have more reliance on the DOC strategy, because it is the one which has the possibility of displaying original content. Okay, so when you use the DOC strategy, NBS will be able to stop NTV from winning, and NTV will be able to increase its winnings. Now, at this particular point, we need to find out, since our focus is on ensuring NTV is going to win, what will be the most probable number of customers or number of viewers that NTV Uganda is going to win, regardless of any strategy that NBS is going to use. So regardless of any strategy that NBS is going to use, NTV Uganda will have to win. Okay. Now we're going to find out if NTV Uganda eventually wins. Okay, what will be the maximum possible number of viewers it will be able to have in thousands. Okay, so that what you're going to do that you're supposed to compute what we call the value of the business. You're supposed to compute the value of the business. So now what you're going to do, you're going to compute the value of the business. Remember the value of the business. Value of the business using mixed strategy is computed, okay, using the same formula as before. Okay, this is shown below. Okay, so we are going to copy this formula here, and we shall use it down here. It is here. We are going to use this formula here. So I shall say value equals to, we look at the payoff matrix value, okay, times oddment value, okay, divided by total oddments. Total oddments is 60, they are here. Okay, so a payoff matrix value is 12, okay, multiplied by the oddment value is 38, okay, 38. Again, you take 6 multiplied by 14, again you take 12 multiplied by 8, you add them together, divided by 60, that should give you the value of the game, So let's do it together and see what we get, okay. If I'm to use this particular logic, okay, what I will do is to do this. I'm going to say, okay, insert an equation. I'm going to insert an equation here. Okay, I'm going to just fly to the left. Okay, and then from there I'm going to insert this one. Again another one. And again another one. No, this one. I think we should leave the way it is. Should be able to get the value of the game. Said is the value of the payoff matrix times the oddment, corresponding oddment. So we shall now, let's look at the first one, which will be 12 times 38. Okay, 12 times 38. It will be 12 times 38 plus. Next is 6 times 14. 6 times 14. Next. 6 times 14. Next we have 12 times 8. 12 times 8. Then everything is divided by what? The total oddments, which is 60. Divided by total oddments, which is 60. Okay, now if you are to multiply this one, this will be equal to, I want to put this article item here. So we shall say, open brackets, 12 times 38, plus, open other brackets, 6 times 14, plus another bracket, 12 times 8 equals to 636. This becomes 636 divided by 60, which gives you, if you divide this one by 60, it gives you 10.6. 10.6, okay? So since the number of viewers are in thousands, number of viewers are in thousands, okay, the game indicates that NTV will be able to win by enhancing its viewership by 10,600 viewers. This is the same as saying 10.6 times 1,000. Okay, times 1,000. If you have to do the calculator, it is times 1,000. It gives 10,600. Okay, yeah, 10,600. So this is how we conclude. And in your free time, you can be able to try, in your free time, you can be able to try to use the second row, 14 times the oddment, 38, 4 times the oddment, 14, 6 times the oddment, 8, divide everything by 60, and you see if you get the same value which we have got here. Okay, yeah, so basically this is how we conclude our discussion on game theory. So as a wrap up, we can say that game theory is a very interesting area. It helps you to come up with the strategies which can help you to make decisions, as what you have just seen in the different scenarios. But one thing you're supposed to put in mind is the flow chart we came up with, and this flow chart helps us to know which direction to take to provide solution to our game theory. Okay, this is a flow chart here which we prepared earlier. This is a flow chart here, and this should be a guiding point when you're dealing with game theory. Okay, this one here. So to have a starting point and ending point. Okay, start, determine saddle point. If it exists, or using saddle point. If it doesn't exist, check if the matrix has a dominant strategy, dominant principle. Use that one to solve. If it doesn't exist, then use the final portion of our solution. And remember, in both cases, you're supposed to compute oddments. I use oddments to get probabilities, and these probabilities and oddments to combine together to get the value of the game. Okay, in both cases. But the procedure of getting oddments is different depending on the number of rows and columns you have. A 2x2 matrix, just get the differences. But in the 3x3 matrix, we saw we have to get the many differences. Okay, yeah, that's how it works. That is all for now, and maybe we shall meet in another discussion in a similar way. Thank you so much, and God bless you.